Hello and welcome. Today we're going to be talking about the properties of harmonic functions. So the question first, of course, is what is a harmonic functions? What is a harmonic function? A function u of x comma y that's is equal to z, and x comma y are an element of w, some open set. And u has to solve Laplace's equation. So u solves Laplace's. Okay, and we can also say that u on the boundary of the open set is equal to some specified boundary value, some sort of boundary condition. Okay, so if we have some boundary condition, okay, and that could be any valid function. So any function that's well behaved, smooth, or piecewise smooth, piecewise continuous, things like that. So again, what we're looking at here are if we have some set like this, an open set in the plane. And then we have around the outside edge here, that's going to be the boundary of w right there. And our function w, or our function u, sorry, is defined everywhere on that set, w. And that is u is equal to x comma y is equal to z, the z value there. Okay, and then on that boundary, there's some specified Dirichlet boundary condition where u is equal to f on the boundary, and I'll draw that in black. Okay, so harmonic function it literally equals a Laplace solution. So harmonic function, that is a fancy name, and that's of course it really emphasizes the specialness of Laplace's equation. So these are very special functions. I like to think of it harmonic. It really invokes this notion of harmony. The fact that they represent sort of a balance point. Or some sort of harmonious function that and also it's invoking this notion of equilibrium, because literally a Laplace's solution is a equilibrium solution to a heat or a wave equation or a diffusion equation. So for all of those things, Laplace's solutions are so special they're given this new term called harmonic. And they play a really important role in all over applied mathematics and physics. And for that reason, they're worthy of study on their own right. And it turns out that they have very special properties. Okay, they have very special properties. And in fact, in this course, we're going to list 5 properties. In this video, we're going to just mention just 2 of them right here. And one of them is going to be really basic, and the next one will be extremely important. And then in each subsequent video, we'll show you one more of these special properties, and how they relate to Laplace's equation and how they relate to physics. Okay, so without further ado, let's talk about the first property. The first property is, again, very basic. We're not going to prove it, but it's just the given a f boundary condition, u of x comma y that solves that exists and is unique for all f. Okay, so that's a very important property. It just means that there is only one function, u of x comma y, for every boundary condition f. And I think that's a very powerful idea here, that this harmonious function that links a boundary condition with its interior. Again, we have this picture here of some set w, and we talk about its boundary, and we have some function that exists, whose values exist on that boundary partial w, and there's only one function in the interior that satisfies Laplace's equation. And I'll draw that surface like that. Like that. So there's only one. And I think that's a really important property. So not only are they special in the fact that there's a one-to-one relationship between boundary condition and the specific harmonic function that we find, there's now another really important condition, which I'll mention now too. And this condition is almost the very definition of a Laplace equation solution, which is zero net flux. Okay, so we'll have this over partial w or any boundary of any subset. So if you have a set u that's a subset of w, and you have partial u is going to be the boundary of u on any, there's always going to be zero net flux. So we have to define what is flux here. And recall from the heat equation. So what is flux? We're going to have that question. So the heat diffusion equation, we know that the flux field is going to be equal to d, negative d, times the gradient of u, where d is some positive constant. In fact, we can just look at, without loss of generality, we can just say that it's equal to the negative gradient. The d parameter doesn't really matter at all. Okay, so we could take that as our flux field. So again, we have our boundary. There's w, and there's the boundary right there. And then what we can do is look at the normal at every point on the boundary. So those normals are always orthogonal to whatever the tangent of the boundary is, like so. So I'm just drawing a sampling of what these normal vectors look like. You can imagine at every point on the boundary, there would be a normal vector that you could visualize there. Like there, okay? All right, so, and then what we want to do is we want to compute the net flux. And that net flux, of course, is going to be something we've learned from multivariate or vector calculus, which is going to be a single integral around the boundary. Remember, we're not passing through a surface here, but rather a contour in 2 dimensions. So it's going to be a single integral around the boundary of gradient u, the negative gradient u, dotted with the normal of the boundary, ds. We're ds now, and I'm going to write that as a green line here, like there. That's going to be this length here, every little length segment of every little piece of the boundary. Okay, so the net flux is always zero for every solution to the Laplace's equation. So it turns out that this can be taken as the definition of harmonic functions. Okay, so it's not just a property or an ancillary property of this, but rather the zero net flux is the very definition of a harmonic function. And so what I want to talk about here is how to do that. And this actually goes into basically a proof of this. So the proof turns out to be really straightforward, and it uses the divergence theorem. Which states that if I have a flux, so there's my flux field, and I've dotted it with my normal to my surface, ds, I can always express a flux in terms of the double integral over the interior of the set of the divergence. Like that. And we all know, right here, that's just going to turn into Laplace's equation as defined. So what we can write is, of course, the double integral over W of, and I can move the negative outside. The negative doesn't matter at all. And then, of course, we know that is zero. The Laplacian is zero by definition of what U is. U is defined as the solution to Laplace's equation. Therefore, we have a double integral over our interior of that. And the negative sign, of course, doesn't matter. All right, so we should also mention there that, of course, this is true not just for W, but for any set. So if I have a U inside of here, here's my U, and then I have the boundary of U, the same could be said for any subset of W. So anything you can think of, this will always be true. And that's because the Laplacian of U is zero everywhere on W, on any subset, including U's boundary, everything. So this definition is really, really important. So it's more than simply a property, but almost like an alternative representation of what a harmonic function is, this zero net flux property. And again, that represents the idea of balance. What we're saying here is that if there is some positive flux into the boundary in some subregion. So, for instance, if I have stuff going in, if I have flow going in one subregion, then it must be true that there is an outward flux in some other subregion that balances perfectly. So at some other point, we're going to have an outward flux. So the outward flux is all through here. So that we're going to assume there that if we were to add up all the lines going into my set and all of the flow going out of the set, those are always going to be perfectly balanced. And that's why we're, again, the idea of harmonic is harmony, of balance, of everything exchanging in equal amounts. That's all is the notion you're coming up with when you're talking about harmonic functions. All right, so I want to give now an example of this property. So the property is as follows. So let's look at a specific harmonic function. I'm going to look at a very special one, x squared minus y squared. So this is called the hyperbolic paraboloid. It's the hyperbolic paraboloid, and note, of course, that uxx plus uyy, well, that's going to be equal to 2. That's the second derivative in x. Minus 2 is equal to 0. So this is, in fact, a Laplace's solution. Now we're going to consider a set W that's going to be the unit disk. So we're going to look at the unit disk at the origin. So what we have here is, and our set is here, and we know this the surface of this function has these paraboloids, or these parabolas that look like a Pringle shape, kind of like so. There's sort of a saddle type shape to it. All right, so now what I want to do, let's explicitly compute the flux. Okay, so it turns out, of course, I can find what I need to compute, of course, is I need to find grad u, and then I have to dot it with the normal. Okay, so the normal, of course, to the disk is just going to be pointing radially outward. And it turns out, of course, that this, of course, is a directional derivative. That's the directional derivative. And so what we can do, and it turns out this is always going to be in the radial outward direction. So we can actually say is this is equal to the partial derivative of u with respect to r when we convert to polar coordinates. So we can figure out what that is pretty easily. So what we can do is actually take x and set it equal to r cosine theta, and y is equal to r sine theta, as follows there. All right, in which case we're going to get u is equal to r squared cosine squared theta minus r squared sine squared theta. We can factor out the r squared, and we're going to left with a difference of squared trigs. So we'll have to do a little trig identity here. Let's remember that cosine squared. So you can probably look up the difference of squared trigs. It's a pretty straightforward identity, but I'm going to get it from the double angle formula. It's easy to do. Right, and then for sine, it's a very similar one, but you take the difference of cosine 2 theta. So there's the double angle formula. Now, of course, what I'm going to do is I'm going to subtract them from each other, and we're going to see that these constant terms will cancel, and they'll be left with cosine 2 theta. Okay, cool. So that's what the output is of that. All right, so now what I want to do, of course, is I want to do the flux integral, which is going to be the integral around W, W's boundary. So this is, of course, going to be the circle. And then what I have here is the gradient of U dotted with N. And again, the negative part doesn't really matter. I could put the negative gradient on there, but we know it's going to compute to 0. We don't care about the sign in that particular case. And of course, ds, that's going to be equal to d theta. okay, because we're talking about a unit circle. And then we already know that this is going to be a 0 up to 2 pi. And then we're going to have the partial derivative of u with respect to r. And then we're going to calculate it at r equals 1. And then we're going to integrate around all of theta d theta. Okay? All right, so there we go. So now we just have to calculate the partial derivative of u is equal to r with respect to r. So we have to remember that this is going to be r squared times cosine 2 theta. Right, and that's because, of course, we have that r squared. That goes there. We also have that cosine of 2 theta, and that goes there. All right, so there we go. And that is simply going to be 2r times cosine 2 theta. Okay. All right, so to finish this one off, 0 to 2 pi, and now we have 2r cosine 2 theta d theta. But of course we're setting r equal to 0, so I have to do a little bit of manipulation here and just set that r equal to 2. I'm gonna clean up my cosine there. I'll just rewrite this. That's going to be 2 cosine 2 theta. And of course this integrates to 0. Of course the antiderivative of cosine is sine 2 theta over 2 times 2. We're going to evaluate it 0 to 2 pi, and then we're going to get it to 0 minus 0 is equal to 0. So of course we check that off. We have truly verified that in this particular answer we did actually get a 0 net flux, and we also know it is a solution to Laplace's equation with a specific boundary condition. I hope this example is just, again, it's just verifying something that we knew is true from the divergence theorem, something we knew is true from these very important theorems in calculus. But it's good to actually go into the nuts and bolts and actually see how it works in a particular example. So I hope you found this video enlightening. In the next video, we'll have several parts. We'll go over many other properties of Laplace's equation. There are many. This is just the first one and probably the primary one I would consider. So I'll see you in the next video.